So you know that the flux density is straight away given phi rho minus 3 whole square into aero cap, and ds will be, so since rho is constant, phi is changing and z is changing, so there is a change in phi and there is a change in z, and since rho is constant, the direction will be aero cap. So the amount of the flux psi is equal to W phi rho minus 3 whole square into rho d phi dz. Aero dot aero will be straight away 1. So and you can substitute the value of rho will be straight away 4, and you can simplify that problem. So 20 into W d phi dz. Phi is varying from 0 to pi. Z is minus 5 to 5. So 20 into pi into 10. So straight away we will get psi will be 200 pi coulombs. So you understood this problem, right?
Yes, sir.
Yeah. Okay, then we'll start with a new concept today. So we'll start with a new lecture. So the same electrostatics part we are going to continue. And in this session, we will try to cover the different types of the charges. And we'll see the Maxwell's equations for static electric fields. And we'll see what is the application of the Gauss law. So first start with the types of the charges. Now voice is clear, right? Any problem you are getting in communication? Okay. So basically you would have been studied that there are different types of the charges were existing. So one will be the point charge, where the charge will be concentrated only at a point. So in case of a line charge, what will happen? You can consider something like this. The charge will be uniformly distributed along a line, something like this. So this is considered as a line charge. Suppose if the charge is distributed in a surface, something like this, so which is called as a surface charge. And when the charge is distributed in a volume, we already seen this as also an example of non-metallic solid sphere. So in a non-metallic solid sphere, the charge will be distributed inside the volume. So that can be considered as a volume charge. So if the charge is distributed line, you can call it as a line charge. If it is distributed over a surface, it is called surface charge. And if it is distributed over a volume, you can say a volumetric charge. When the charge is concentrated at a single point, you can easily say the amount of the charge will be q coulombs or something like that. But whereas when you go for the line charge, the parameter what it will characterize is the rho L. So rho L will be also called as the line charge density. So the line charge will be always characterized by the line charge density. So how the line charge density will be defined as rho L. When you take a small differential length along a line, so let me call it as dl, the amount of the charge present in this differential length is basically called the line charge, which means that, so you can say that in this particular length, there will be a small amount of the charge. I'm calling it as delta Q divided by in a length of delta L, where delta L will be very, very small. So this is called your rho L. So in other words, you need not to get confused here. So the line charge density represents the charge present in a small length. So that is the charge divided by the length. The length has to be as small as possible. So the charge divided by the length is basically called your line charge density. So rho L will be defined in terms of units. If we consider, it will be coulombs per meter. Now, can you tell me what will be the total charge if we know the value of rho L? Suppose if you know what will be the value of charge density, how to find out the total charge present on the entire line?
Rho L into length of the line.
Rho L into total length of the line, right? So in terms of integration, I can put that will be straight away integration of rho L into delta L, right? So when you are integrating the line charge density over the whole length, you will get the total charge present on the line. So I can give some examples for the line charge also. If we see the electrical filament inside a bulb, so what will happen? There are so many number of electrons is accumulated on the filament. So you can see here the filament is a small conducting element. So we can treat it as a line charge. So the line charge density is basically how much amount of charge is present in a small differential length. So the units will be coulomb per meter. So to get the total charge, integrate the line charge density over the whole length. So similarly, there will be another quantity called surface charge density. So what will be the surface charge density means? For an example, I have considered a small differential surface here. You can see in this case, but the charge is distributed over the whole surface like this. So the surface charge density is basically defined as how much charge is present in this differential area. So let's say delta Q is the charge present and delta S is the area of this particular surface. So the amount of charge present in a small differential area is called surface charge density. And you can see that the units will be in the order of coulomb per meter square. So in the same proportion, to get the total charge Q, if you know the value of rho S, you can straight away integrate. So straight away integrate the value of rho S over the whole surface. So when you integrate the rho S over the whole surface, you will get the total charge within this surface. So the simple example for the surface charge. Can anybody give the example for the surface charge? Capacitor, correct. So when you have a capacitor, when you apply a AC voltage across a capacitor, the charge will be distributed on each conducting plate. So if you take a parallel plate capacitor, based on the voltage you are applying, the charge will be induced on each plate. So that kind of distribution is said to be the surface charge. So similarly, what about the volume charge? So the volume charge density rho v will be straight away you can call it as the amount of charge delta Q present in this differential volume. So you consider I have taken a small volume here. So delta Q divided by delta V represents the volume charge density. And the units will be in the order of coulomb per meter cube. So in the same way, the total charge Q can be written as integrate the value of rho V over the whole volume. So the simple example for the volume charge we already seen in the previous question. If you have a non-metallic solid sphere, the charge will be uniformly distributed inside the volume. So that can be considered as a volume charge density. So finally, what is the summary here? If we have a point charge, the magnitude is Q. If we know a line charge, the value of Q will be straight away integral rho L into delta L. If it is a surface charge, it is same as rho S delta S. Volume charge, triple integral rho V into delta V. So this is a type of charges and their relation. So understood, any questions you can try to clarify now only. So please ask any questions if you have. Shall I move on to the next one then? Volume will be non-metallic solids portion. Yes, exactly. When I say a solid sphere, then only the charge will be distributed right inside. Suppose if it is a hollow sphere, you cannot have the charges present over it, right? So when I consider a metallic solid sphere, then only the charge will be distributed in a volume. So the answer is volume will be definitely, it's a solid portion and it should be a non-metallic. Correct. So we'll find out the electric field intensity due to different type of charge distributions basically. So we'll come back to this slide later after that, after seeing the Maxwell equation. So see the Maxwell equation first here. So as I said in the previous class, the Maxwell's equations are not so complicated. Just with the help of understanding of the simple physics, we are able to derive the Maxwell's equation. So to understand this, first you can see here, there is a charge located here. You know that whenever there is a charge present here, it will obviously create an electric flux, which will be divergent in nature. So the nature of the electric flux lines will be always divergent in nature. So divergent means it is moving away from the source and it is continuously radiating away from the source. So the electric flux lines are always said to be a divergent nature. So in other words, there is no rotational nature for the electric field. Will you agree with my statement? There is no electric field exists for, there is no rotational nature exists for electric fields. Is my statement correct or not? Based on understanding of physics. Yeah. So when you consider any electric flux, you can see here, there is always a divergent nature exists because electric flux lines cannot form a closed lines like a rotational nature. So whenever, let me consider the electric field vector E. So when there is no rotational nature for any electric field, we have already seen in the vector calculus part. So when there is no rotational nature, that means the curl of that vector will be 0. So based on the simple physics, we can say that there is no rotational nature exists for electric fields. So I can say the curl of electric field intensity or electric flux density, you can say. That will be always a null vector. So this is your first Maxwell equation. Now, the same equation we will try to write in terms of the integral form. So what I was doing for the same equation on both the sides, I was multiplying with net area. So in a mathematical form, I can write the left hand side as a double integral curl of E into ds will be equal to, right side multiply with 0 will be straight away answer will be 0. So instead of area, I have written it as a double integral curl of E into ds. So using Stokes theorem, how to convert the surface integral back to line integral? So what is the Stokes theorem says? The line integral can be converted to the surface integral. So what I was doing using Stokes theorem, whatever the surface integral is there, I was converting it back to line integral. So something like this. So integral E dot dl and the line has to be 0. So using the Stokes theorem, the surface integral I have converted to the line integral of electric field intensity and the line has to be closed using the Stokes theorem. So this is your first Maxwell equation in integral form. So what is this equation says here right now? You can clearly see the electric field intensity is volt per meter and the length will be in the order of meters. So finally it gives some amount of voltage, right? So E dot dl represents a quantity called voltage. So whenever it is a closed loop, the net voltage in a closed loop will be 0. So that is what you have been verified even in case of KVL, right? So if we have the Kirchhoff voltage law, what it says? When you have a closed loop, the net voltage in a closed loop will be obviously 0. So you can see here, this is the proof for your Kirchhoff's voltage law. So E dot dl represents a voltage quantity and whenever the loop is closed, the net voltage will be always 0. So that's what I have given here. The line integral of electric field intensity in a closed loop will be always 0. So you got the point here. Any questions you have? So whatever you studied in your network regarding the KVL, now we are able to prove that with the help of the Maxwell's equations. So did you understand? So KVL thing, please explain. See here, the same thing I was using the Stokes theorem. You are able to convert it back to the line integral. That part understood or not? Using the Stokes theorem, I was converting into line integral. Is that part clear? Yeah. The next thing was, you can see here what is E dot dl. So if we see the unit of E dot dl, what will happen? Volt per meter into meter. So it gives some amount of voltage. What is the condition? Integral E dot dl is equal to 0 and the line has to be closed, right? With the help of units, you found that E dot dl represents a voltage, right? So whenever it is a closed loop, if you are calculate total sum, integration is nothing but sum. So the sum of voltages in a closed loop will be always 0. So that is what your Kirchhoff's voltage law says. Now is it clear? Yeah, good. So the first Maxwell equation says that, if I can summarize it in a simple words, there is no rotational nature exists for electric fields. That means electric flux lines are always said to be divergent. So since there is no electric flux lines exist, you can see here the curl of the electric field intensity will be 0. In other words, electric field intensity is said to be conservative or irrotational. So when you multiply with area on both the sides and convert it back, you can say that the net electric field intensity in a closed loop is always 0. Okay. Next, move on to the next slide. So what is this second Maxwell equation we already seen in the case of Gauss law, right? The same thing I was projecting here. So this is the charge which is located, and because of this charge, the flux will be radiated in all the directions. And I try to capture the flux using a closed surface, something like this. So we already seen when any charged particle is enclosed by a closed surface, what is the Gauss law says? The net flux leaving the surface will be exactly equal to the amount of the charge present inside it. So what is the meaning we have seen? The value of double integral, the flux density d dot ds will be exactly equal to the charge enclosed in it, provided the surface has to be closed. Right? So this is your second Maxwell equation, which already we have discussed. There is no doubt about it. Now, using the divergence theorem, since the surface is closed, I can convert the surface integral into volumetric integral, right? So how to convert that? So the surface integral will be converted to the divergence of that vector multiplied by the differential volume is equal to, what will be the total charge here? In this case, the total enclosed charge will be same Q. So you know that the value of Q can also be written as triple integral rho v into delta v. So where we have seen in a volumetric charge, to find out the total charge, it will be straight away integrate the value of rho v over the whole volume. So when you see the relation between this one now, if you try to compare these two, what is the conclusion you are getting? The divergence of electric flux density will be equal to rho v. So where rho v is basically said to be the volume charge density. And the units are in the order of coulomb per meter cube. So this represents the Gauss law in case of a point form. Point form means either divergence or curl. And this represents the Gauss law in case of an integral form. So once again I was summarizing, when you try to enclose any charge with a closed surface, the net flux leaving the surface will be equal to the charge present inside it. So that is what this equation gives. So since the surface is closed, you can apply the same thing using the divergence theorem. So, and at the same time, the value of Q can be written in terms of volumetric integral like this. So you can compare these two equations, you will get del dot D is equal to rho v. This is your second Maxwell equation. So these are the two Maxwell's equations which will be valid for static electric fields. So if you go to the time varying electric fields, again these equations may change. That we'll see in the next portion. So if you summarize the two Maxwell's equation, the first Maxwell equation will be curl of E is equal to 0, and the second Maxwell equation will be del dot D is equal to rho v. These are the two Maxwell's equations for static electric fields. So any questions, you can clear it now. So if you need any explanation or any concept, I can explain. Yeah, clear. Just a minute. Give me. Okay, now we'll go back to this one, electric field intensity due to the different type of charges, right? So in case of a point charge, we know what is the electric field intensity. That will be Q by 4 pi epsilon R square into air cap. So if you want to calculate using the line charge, you know that in case of a line charge, the charge will be Q is equal to integral rho L into delta L. So what will be the electric field intensity now? The same thing. Since Q is unknown here, the Q should be replaced with the integral rho L into dl. So that will be integral rho L dl by 4 pi epsilon r square into radial direction. So similarly, if it is a surface charge, so what about the value of Q here? Q can be written as double integral rho s into delta s by 4 pi epsilon r square into air cap. So the same equation I was writing in terms of point charge, but replacing the value of Q accordingly. So if it is a volume charge, so Q will be replaced with triple integral rho v into delta v by 4 pi epsilon r square into air cap. So this is represents electric field intensity due to the different type of charges. So any questions in this slide? Based on the help of the point charge, just replacing the value of Q, accordingly. You know the value of Q in line integral, surface integral and volume integral. Yeah.
Sir, in this case,
Yeah.
that AR cap means it's not that spherical one. It is that along
No,
the.
air cap is just only I was representing it as a some radial direction. It's not a small r, you can see.
Okay, okay.
If it is a spherical, the small r represents the radial direction, right? Whatever capital R I was representing, it's a radial direction. It may not be r always.
Okay, sir.
Right. Now we'll see the main important topic in this session. That is nothing but the Gauss Law applications. So what is basically the Gauss Law says? You have seen here, right? The double integral d dot ds is equals to Q. So using the Gauss Law, if you know the type of charge, let us say Q is known here. So once the value of Q is known, you can already define what will be the electric flux density, right? D. So since Q is known, you know the value of D, and the value of D is same as epsilon times E. So once the value of D is known, you are able to define what will be the electric field intensity. So when I say the Gauss law of application, it is mainly to determine the electric field intensity due to the different type of charges. So for this, to make the problem simpler, I have given the two steps which you need to follow when you are finding the electric field intensity using the Gauss law. In other words, I was giving a simple hint. Suppose even in your gate problem, if they say find out the electric field intensity due to so and so charge, the first thing which comes to your mind was it is an application of the Gauss law. So to find out the electric field intensity, you need to go in a step-by-step sequence. So the first step is what? Enclose the source with a closed surface, provided the surface has to be symmetrical. So suppose if we have a charge, the charge has to be enclosed with a closed surface and that surface should be symmetrical. So what do you mean by the closed surface here was, whatever the surface you are closing it, that should be purely capturing the total flux. So whatever the flux generated from the source, if the closed surface should be able to capture that, then only you can say it's a closed surface. And I will tell you the symmetrical meaning later. And the second thing was, you can straight away apply the Gauss law. So first, let us try to apply the same thing. Consider the case 1. This is the electric field intensity due to point charge. So we already know the electric field intensity is Q by 4 pi epsilon r square into AR cap. That we try to prove with the Gauss law. So this is the charge which is located here of magnitude Q. And my intention is I need to find the electric field intensity at a distance of r. So what is the first thing? Enclose this point charge with a closed surface. So this is the surface which I am calling it as a Gaussian surface. So this is a closed surface, right? Because whatever the flux is generated here, I was able to capture. So my first condition has been met. What about the symmetrical? Can anybody say what do you mean by symmetrical? What is your understanding about symmetrical? Uniform shape in all directions. Okay. Divided into equal parts. Okay, let me define this. So when you have this particular surface, I can call this as a closed surface and it's a symmetrical surface. Symmetrical means if you take any point on the surface, it should be equidistant from the source. So when you take any point, whatever the distance here, similarly if you take a point here, it should be same distance. If you take a point here, same distance. So the symmetrical surface represents the distance from any point on the surface to the main source will be same. That kind of surfaces are called symmetrical. So whenever the point charge is here, I can capture it with a sphere. So can I consider the sphere as a symmetrical surface now? Is it satisfying the relation? So this is your point charge and you try to enclose with a sphere. Is it a symmetrical case now? Yes or no? Yes, because whatever the point you have considered on the surface of the sphere, it is at a equal distance. Now, suppose the point charge is here. I was trying to enclose this point charge with a square. Can you say this square is a symmetrical surface with respect to the charge? Is it correct? No. No, because you can see here if you consider a point here, the distance is small. Whereas if you consider a point here, the distance is large. So the distance keep on varying from position to position, right? So this distance is quite more and this distance is quite less. So the symmetry is not satisfying. So the symmetry has to satisfy means the distance from any point on the surface to the charge must remain same. So in this case, to capture the flux due to the point, I have taken a sphere into consideration. So you have considered a closed surface and the symmetrical part, both are satisfied. So the next thing is what? Apply the Gauss law. So what the Gauss law says, double integral d dot ds is equals to q enclosed. So since you can say here the flux is always there, the magnitude of the flux I can take it constant, and the surface area of this particular sphere is, because r is the radius of the sphere, you can say, so the surface area of the sphere will be 4 pi into r square is equal to, so the total enclosed charge will be straight away q coulombs, right? So the flux density will be straight away q by 4 pi into r square. So q by 4 pi r square, you can say the flux density is same as epsilon times E. So hence electric field intensity will be q by 4 pi epsilon r square. This is the same thing we have got with the Coulomb's law also, right? So in that way you can verify the Gauss law and the Coulomb's law. And the direction, if you want to find out, the direction will be always radially away from the source if the charge is positive. The same logic will be valid here. So as an example, I was putting radially away from the source. We will see once we will discuss the problem, so you can clear with the direction part. So if the steps are clear, so the first step is enclose the source with a closed surface. That surface should be symmetrical also, and apply the Gauss law. So when you apply the Gauss law, you will be able to find out the flux density. So the flux density is epsilon times E. So you can easily able to define what will be the electric field intensity. So is the steps are clear now? If the procedure is clear for you? Now we will try to apply the same logic to the line charge now. So consider there is an infinite line charge. So you can see here this is an infinite line charge where the charge is uniformly distributed. And now I want to find out the electric field intensity due to this line charge at a distance of rho. So this is your line charge and I want to find out the electric field intensity at a distance of rho. First thing is what? Step 1. The line charge should be enclosed with a closed surface. So since the line charge has to be enclosed with a closed surface, I have taken a cylinder something like this. So the cylinder is able to capture the total flux. Is it correct? First of all, can you tell me what will be the flux line's direction here right now? So since the line charge is something like this, the flux will be radially something like this. It will be radially. So since the flux is generated radially, I have considered a cylinder to capture the total flux. So please answer me, is the cylinder satisfies the condition of symmetry? So when you have a line charge and you try to enclose with a cylinder, is it satisfying the symmetry? Yes, because you can assume that this line charge is located on the axis of the cylinder. So whatever the point you move on the cylinder, you are always at a equal distance, right? So the distance rho remains same here. So whatever the distance if you move here, rho remains same on a cylinder. So I can say the cylinder is an example of the symmetrical surface. So cylinder is you have considered and it satisfies the symmetry also. First of all, you tell me what will be the total charge enclosed in this. So since it is an infinite line charge, we can see here. So the total charge Q can be written as integral rho L into delta L, where I was integrating from 0 to h by considering h is the height of the line charge and h tends to infinity. Is my assumption correct right now? So I was integrating over the line charge density over the whole length by assuming h tends to infinity. So anybody is having objections here? Ideally speaking, the charge is infinite, but to make it as a finite quantity, finite integration, I was integrating from 0 to h where h tends to infinity. So is my assumption okay? Is it correct? Yes. Yes. So I can, to make the integration finite, I have considered h is the height of the cylinder or the height of line charge by assuming h tends to be infinity. So next, what is the Gauss law now? You already considered a surface, so then straight away you can go for the Gauss law. So double integral d dot ds is equal to q enclosed. Flux density constant. Flux density to what is the surface of the cylinder? So the cylinder is having a radius of rho and the height h. So the surface area will be straight away 2 pi rho L into h. Both h to infinity. So h gets cancelled. So the flux density will be written as by 2 pi rho L by 2 pi times E. So the electric field intensity can be written as rho L by 2 epsilon into and the usual I can say direction of electric field intensity will be always radial. So any questions in this? So this gives the electric field intensity due to an infinite line charge. So first thing was the line charge is enclosed with a cylinder and the cylinder satisfies the condition of symmetry. Find out the total charge enclosed in that. So that will be the integral of line charge density over the whole length. So I can take in h is the height of the line charge by assuming it to infinity. Then you apply the Gauss law. So the surface area will be 2 pi into radius into h and charge will be rho L into h. So you can do that, the electric field intensity equation, this you will get it like this. So rho L by 2 pi epsilon into rho, and the direction will be radially away from the line charge. So is it clear now? Okay, I will move on to the next one now. So this is electric field intensity due to the surface charge. This is also an infinite surface charge I have considered. First try to see here. So this is the charge, surface charge, where the charge density is rho s coulomb per meter square and the area is A. So this sheet is having a finite amount of the charge. Now what will happen? Whenever you are having any surface charge, the flux will be radially away. So what is the meaning? There will be some amount of the flux in the upward direction, some amount of the flux in the bottom direction, right? So first thing, to enclose this surface charge, I have placed one plate on the top side and one plate on the bottom side. So can you say this top plate and bottom plate together can be considered as a closed surface? So when you have a surface charge something like this, the configuration of the top plate and bottom plate together, I can say it as a closed surface. Is it correct? Or still some more surfaces has to be concerned?
So it's a thin plate, the one that is containing the charge.
Which one? No. It is having a sufficient area of cross section. It is not, thickness is small, but the area is larger.
Okay, then it's fine.
In that case, what I mean to say, generally, what is the meaning of closed surface? So in our understanding, closed surface is something like a sphere or something like a cuboid. It will be
Yeah.
closed in all the sides, right? That is physically closed. But what happened
Okay.
here, I can say, if you say here this configuration, this is not physically closed, but electrically closed.
Yes, because flux is always perpendicular to the sheet. That's why.
Correct, exactly. Since the flux is always perpendicular, are you able to capture the total flux using this configuration or not? So whatever the flux generated in the top plate will be captured by this top plate. The flux in the bottom direction will be captured by this plate. So do you have any flux in the side directions? Do you have any flux something like this? Yes or no?
No, sir.
No. Because when you have any charge, the charge will be always radially away from that. The flux lines will be radially away. So you don't have the flux in the same direction of the sheet. So you need not to put any plate in these directions. So it doesn't require at all. So since the flux is existing only in the top and bottom direction, you can put one plate on the top and one plate in the bottom. So even though it is not physically closed, but as per the definition, it satisfies the electrically closed. Because all the flux lines will be captured by this both top plate and bottom plate. And how will you ensure the symmetry in this case now? Can anybody says how the symmetry can be ensured here now?
We have to take always the direction of the flux to measure the distance.
That means whatever the distance at which the top plate is placed from the main surface charge, you should always place the bottom charge also at the same distance. So whatever the distance from here to here is same as the distance from here to here. It's just only the placement. So ensure that the distance from top plate to main source will be same as the distance from bottom plate to the main source. That way you can ensure the symmetry. But of course, that distance doesn't matter. You can see that after the end of this derivation. And at the same time, you need to ensure that the top plate and the bottom plate both should also have the same area of cross section as the original charge, right? Suppose
Yes,
if this if this charge area is more and this area is less, some flux lines will be missing out. So to capture the total flux, the area of the top plate and the bottom plate must be same as the area of the original sheet. So that will ensure that the total flux will be captured. So you have considered the closed surface and the symmetrical surface. Now, what will be the charge present on the surface now? So this is the surface charge of density rho s and the area A. So using surface charge, we already know the total charge can be obtained by integrating rho s over the whole surface. So since I already given the surface area is A, you can say the total charge will be rho s into A. Which means this is the amount of the charge present on the whole surface. So you know the rho s and A, multiply rho s with A, you will get the total amount of the charge. So what about the flux leaving the top plate and bottom plate? Both will be in the same direction, right? So I can say the total flux using Gauss law. What is the condition? Double integral d dot ds is equal to q enclosed. So what about the flux leaving the top plate? Is same as the flux leaving the bottom plate. So I can say the total flux will be 2 times of the flux density multiplied by the area. So since there are two surfaces, that means top surface and bottom surface, since the same amount of flux is leaving this and this, what I can say, the total flux can be written as 2 times of the individual flux passing through either top plate or the bottom plate. So let me write. The flux passing through the top plate will be, you can see here the flux density is a constant and the area is straight away A. So this is the same flux which is passing through the bottom plate also. The flux density is D and the area is A. Right? So what is the total flux here now? So the total flux will be the flux passing through the top plate plus the flux passing through the bottom plate. So I can say 2 times the flux density into A is equal to Q. So 2 into flux density into A is equal to, so Q value will be given by rho s into A. Already you can see this equation. So A gets cancelled. So the flux density will be exactly rho s by 2. So which is same as epsilon times E. So the electric field intensity due to a surface charge is given as rho s by 2 epsilon. So this is the formula, and you can see the direction part. The direction part will be always radial.
Sir,
Yeah. Any questions, please?
so we have a flux like top and bottom. And the charge does not get
Yeah.
divided, means in top and bottom 50-50. It is not like that.
Charge means charge density, you can say, because whenever you are always talking about surface charge, right? It is
Okay.
not, you cannot measure the charge, right? When you say the exact amount of charge, it will be concentrated at a point. Suppose if you say the charge is distributed on a surface, you should not say the charge. You can say the charge density.
Okay, sir.
Right.
Got
So that's what you have seen. Whatever the point you told was correct only. So whatever the charge density I was getting, equally distributed. That is called rho s by 2. So you should not say q by 2 here. Instead of that, you can say that density will be divided. So
Okay.
here you will get rho s by 2 and here you will get rho s by 2. Clear?
Yes, sir.
Yeah. Any other questions you have? Now you can see the important conclusion here. I already told you, you need not to place, in this case, the top plate and bottom plate can be moved further away also. That means this can be kept at some 30 meters and this can be kept at 40-meter distance from the main source. The reason because you can see the equation here. There is no electric field intensity which is a function of the distance. So which means that when you have a surface charge something like this, irrespective of whether you are closer to the surface or far away from the source, the electric field intensity remains same. So in other words, electric field intensity is independent of the distance. This is quite strange when you compare with the point charge and a line charge. So in case of point charge and line charge, it's purely a function of distance. But whereas in case of surface charge, whether you are closer to the source or far away from the source, the magnitude of electric field is same. Clear? Is it clear? Somebody is asking example. Example for what? No, what I was saying here, see here, when you have a surface charge something like this, see here, this is the sheet, and which is distributed with a finite amount of the charge, which means that whether you are here, when you are finding the electrical intensity here, or somewhere here, or here, the magnitude of electric field intensity at all the points remains same because of the constant magnitude. And for if you want to see the example for this, you can consider an example of a capacitor plate only. So if you have a capacitor also, there are two surface charges which will be existing, right? So because of that, you don't have a electric field continuously over the whole distance. That we'll see an example when was discussing the problems also. So when you consider only one metal plate is present, there are no other metal plates nearby, then electric field will always exist, and irrespective of the distance, the magnitude will remain same as long as only one metal plate is there. The moment once you put another metal plate in picture, the electric field will be confined only to a particular zone. So that's what you can see in case of a capacitor. So in case of a capacitor, one will be the positive charge and other one will be the negative charge. In this case, the electric field is confined only between the plates and you don't have the flux in this direction and this direction. We'll see with an example for this when I was discussing the problems. So clear? What is the summary right now? So in case of a point charge, if you summarize it, the electric field intensity will be Q by 4 pi epsilon r square. This is the magnitude. And in case of a line charge, and of course it is an infinite line charge, the value will be L by 2 pi epsilon times rho. And in case of a surface charge, the electric field intensity will be rho s by 2 epsilon naught. So in all the cases, the direction will be radially away from the source if the source is positive. So is it clear? Shall we start some problems on this? So shall I discuss some problems now? Based on whatever
Yes.
we have seen the different type of charges, Maxwell's equation and the Gauss law. So with respect to these three topics, we will try to discuss a few problems on this. So read the first question. So there is a metallic sphere of radius A is distributed with a charge of Q coulombs. And then determine the electric field intensity when R less than A and when R greater than A. So the first case, R less than A. So R less than A means, so this is your metallic surface, right? And the radius of the metallic sphere is A. And you have considered a surface within the metallic sphere only. So this is your Gaussian surface with radius of R. So the first thing, what is the Gauss law says? As I mentioned you in any problem, if they are asking you to find out the electric field intensity, it is straight away the application of the Gauss law. So there is no second thought about it. If you want to find the electric field intensity, immediately apply the Gauss law. So this is a sphere of radius A distributed with Q coulombs. And when you consider an inside surface, what about the electric field intensity? So using Gauss law, what is the condition? Double integral d dot ds is equals to Q enclosed. So which means that the flux density is a constant. Can you tell me what is the surface area here?
4 pi r
Please answer. 4 pi r square. You should remember this surface area should be surface area of the Gaussian surface. So whatever this closed line indicates, right, that represents for the Gaussian surface. So the flux density d into 4 pi r square is equal to, so what is the amount of the charge present inside a metal? We have seen the problem already.
0, sir. 0.
0. Since it is a metallic sphere, there is no charge inside it. So what is the condition now? The flux density will be 0, which means that epsilon times E will be 0. So when you consider inside the sphere, there is no electric field intensity. R less than A means inside. So repeat the same thing when R greater than A and try to tell me the answer. So the same thing, this is your metallic sphere of radius A, and this time the Gaussian surface is outside. This is of radius R. What is the condition? Double integral d dot ds is equals to q enclosed. So this is the same thing, right? The flux density remains same, and the surface area is also 4 pi r square because for the Gaussian surface. And how much charge is enclosed here? What will
Q,
be the
sir.
charge? Q. So straight away the flux density will be Q by 4 pi r square. So which is same as epsilon times E. So the electric field intensity magnitude will be here Q by 4 pi epsilon r square. So this is same as your point charge. Now I will try to put the same thing in case of a diagram. So what will happen here? So consider this is your electric field intensity and this is your radial distance. And let me assume this is a point A. This represents the A, which means on the surface of the sphere. So when you are moving from here to here, your value of R will be lesser than A. So when the value will be lesser than A, the electric field intensity will be 0. So you don't have any electric field, straight away it is 0. So what will happen when you are going more than away from, if R is greater than A? So you can see here the electric field is inversely proportional to 1 by R square. So which means that exactly at A, you will have a maximum electric field. And when you are moving away from A, it is decreasing something like this. So this gives the profile of electric field with respect to the radial distance. And the maximum electric field lies on the surface of a sphere. So this is your E maximum, which will occur when R value is exactly equal to A. Clear?
Yes, sir.
Okay. So do the same problem by considering it as a non-metallic solid sphere. So this you please take time and try to tell me the answer. So case 1, when R less than A. When R less than A means inside the sphere. So this is your non-metallic sphere of radius A. And the Gaussian surface is inside, something like this. This is of radius R. The same thing, double integral d dot ds is equal to q enclosed, and the flux density is a constant, d is a constant, take it out, and the surface area is same as 4 pi r square. So what is the amount of the charge present in this Gaussian surface? Can you tell me what is the amount of charge? Q. Now, because it is a non-metallic sphere, I told you, right? Based on the volumetric proportion you have to take. Right. So Q, the same thing again, you recollect it. 1 by 3 4 A cube is the volume where the total charge Q will be present.
Yes.
But what is the volume of this surface sphere right now? You are able to capture a volume of 4/3 pi r cube, right? So how much charge is present right now? That will be same as Q into R cube by A cube. You understood?
Yes, sir.
Yeah. Then you can simplify it and you can tell me the answer. So R square, 1 R will be left over here. So the flux density will be QR divided by 4 pi A cube. So same as your epsilon. So I can say the electrical intensity is nothing but QR by 4 pi epsilon A cube. Case when R less than, what will happen when R? So this is your material distributed with Q coulombs and enclosed with a there is some problem in the writing game.
Hello.